the OCaml language with a language people tend to do a competition with, which is Haskell. Both of them are functional languages. Both of them are statically typed. But on one side, OCaml has a module system, which Haskell hasn't. And on the other side, Haskell has type classes, which OCaml hasn't. But on both sides, the communities want each other feature, and we can see on various forums people talking about emulating the other feature with the one they have. And this shows like there's kind of frustration in the communities of not having both functionalities at the same time, but the problem is they're not compatible due to various problems. And there has been a proposal 10 years ago of emulating type classes with implicit module arguments, such a way a bit Scala-like, and this will be an idea to solve this problem. This proposal has been done by Leo White, Frederick Bourg, and Rémy 10 years ago at the ML workshop called Modular Implicits. So the idea is we have a module system with the way it is now in various languages. So you have signatures and you can define various modules and functors, and you can declare them as implicits. For example, here I define a signature for printing a type. And then you can define a function with an argument you label as implicit, and this is a modular argument. Such as when after you use this function, you can omit the argument and actually have an equivalent of type classes. So here, you're for printing a list of integers. But the good thing is you can also instantiate the argument by hand in opposition to type classes, so you can do more things, because it's an implicit argument and not a real type class. So this proposal has been done 10 years ago with an initial prototype, but it was more a proof of concept. Since then, over the last 2 years, there has been an implementation of modular explicits, so it is the elaboration language for modular implicits. Then comes the elaboration. So you need to infer the modular expression, and this is what I'm going to present you today, because there has been, over the last year, an implementation of modular implicit and a formalization of it. And in the future, we'll still need to fix the problem of the interaction between type inference and elaboration of modular expression. So for the elaboration, the idea is to add to the language a new feature which is the idea of elaborating module expressions. So we add a new construct, underscore, which is always followed by a signature. And then we have a set of modules, including functors, that we can use for synthesis and, of course, for related signature. And then from this, we're able to elaborate the whole modular expression with only applications. The reason we use application is because it's easier to infer. And so in this case, we're going to infer the module defining sets for pairs of Boolean and list of integers. This can be quite complicated to write by hand, but we're able to infer it fully. But in the end, we still have a set of constraints we want for the solution. We want it to be sound. We want to infer a well-typed solution. We want the inference to be deterministic, to have a deterministic semantic in the end, and not have a different behavior for a program at each compilation time. And we will hope that our inference is also complete and find all possible solutions, but sadly we will see that's not the case. So for soundness, the idea is we're inferring modular expression, and we're just having a subset of the whole typing rules for modules, only applications of modules. And this gives us a small set of rules, and with that we know that we're sound, because we can infer a module only if it has a valid type for the asked signature. For determinism, we just add the constraint that a solution is valid only if all possible solutions are optionally equivalent to the one we take as the valid solution. The fact that we want something optionally equivalent is the biggest relationship we can have. We can just take a smaller restriction and we don't lose determinism. We just have a few cases that will be rejected that could have been accepted. For example, in OCaml, we want to have an observability equivalence inference just based on the location of the definitions and not look at the exact code. Then for completeness. So I'm going to take a small example where I want to infer a module defining comparison on list of integers. So for this, I create a small search for the signature. And I can see that I only have one solution for this, which is calling the list comparison functor on an argument of signature of comparison on list of integers. Then I can apply my same functor once again, and then I only have one solution, which is the module int. So I've done an inference. But what happens if I take a bit more complex example? So I'll take a signature t, which can be abstract, and I also take a functor from t to t. And if I ask for a module of signature t, then I have, which is applying the loop functor to a signature t, which can then be inferred as applying the loop functor to a signature t. And this starts to pose a bit of problem because we're not progressing. And this might cause a divergence in the compiler, so the compiler rejects it by saying that, oh, it's not able to guarantee that the search is going to terminate, so it's stopping the search. And so this example is rejected. Whereas we could have used fixed point analysis, saying that there was only one solution, or just saying there was no solution because we don't have an initial way of building a module of type T. So this is a bit of a completeness problem. But for the termination guarantee, how do we check this? So we need a termination criteria, and the idea is to define partial order on signatures and ensuring that all recursive calls are strictly decreasing for that partial order, and we also want this order to be a well-founded order, so that the search is going to terminate. We also want a few properties for this order. The idea we want to know that comparing integers is a smaller signature than comparing list of integers. The idea is that it's really likely that when searching a list comparison on list of integers, we will recursively reach integers. So we want to consider that this case is strictly decreasing, otherwise many examples will get rejected. In the same way, we want to say that int list is smaller than any type, because specifying type might be progressing in the search. And so to build such an order, the idea is we define a metric on types, and we use the order on ordinals. The idea is that if we have a static type with a certain depth, we define the metric as the depth of the type. And if the type is not static and contains type variables, we take the depth times omega as the depth, and this creates the order that preserves the rules presented above. And then this defines an order on one type, and a signature contains many types. So we can compare all types of signatures together and use an order on those, such as punktwise or lexicographic, depending on what we want. The whole search is parameterized on this termination criteria, so depending on what we want, we can choose a different one. So we said that all recursive calls must be decreasing. So I'm going to take a new example with, once again, the signature show for printing a type, and a functor from list that says that if I'm able to print a list of type T, then I will be able to print the type T by just printing a singleton. And then I'm giving also a module that explains to me how to print a list of integers. And then I want to print integers. So it's a singleton, a singleton, a singleton of the integer. It's easy. But if I'm doing this search, I need to start by calling the fromList functor on printing of list of integer. And this fails because we're not decreasing. Int list is not smarter than int. So this is an incompleteness problem that comes from the termination criteria. However, we deem that such examples are not likely, so we don't care that much about it. And just in case somebody happened to stumble upon this incompleteness problem, there's still the solution of writing by hand the modular expression compared to type classes where you cannot have any solution to a problem if the inference fails. So another problem that arises with inference is the case of functor with multiple arguments. So I'm going to take a functor f, which takes two arguments, an argument a that defines arithmetic on a type, and I have many solutions for this argument. But I also have a second argument s, which defines sets on the same type, and I know which kind of set it is because the return type of functor constrains this type. And if I try to infer the first argument first, I will fail because I have two solutions. On the other side, if I start by the second argument, I only have one solution, I can infer it. This gives me additional constraint to infer the first argument. So in this case, I have one order that is valid, while the other will get rejected by the type checker. And so I don't want the user to take that into account when writing their functors for the order in which they write the argument. So we don't want to constrain the inference of the arguments with a specific order. So we just said that if I have a functor with two arguments, fixing left to right or right to left, this poses an expressivity problem because the user cannot write the program they want, even if they're sound, because the inference is not strong enough. A way around this problem will be to do multiple passes. So I have a functor with two arguments, I can try to infer argument 1 and argument 2, and then if I have inferred at least one of both, but not the other, I can try once again to infer the argument that has not been inferred with a new information. However, this requires me to do 3 inferences for only 2 arguments. And this poses a complexity problem because I'm quadratic. Another guess will be to infer all pairs of arguments possible. So I look at all the solutions for 1, all the solutions for 2, and I try to match them together. But this poses also a complexity problem. I'm once again quadratic. So the solution we propose is to have a dynamic inference with incremental search. So for this, we define a state of the search, which contains a targeted signature, the set of currently valid solutions, an explored space of modules that can be looked on to find more solutions, a focusing point, which is the module we're actually looking at to know if it's a valid solution or not, and also a name, which is a typing artifact. And with those, we then have a set of reduction rules, which can go from a state to another one with various constraints and conditions. However, this state has many things in common. For example, the context, the name, and the targeted signature never change in one direction, so we just omit them in the rule. And the set of constraints that comes from a context, we're going to move it to the size for presentation reasons. So I'll now take another example to explain to you how we use this state and the reduction rules. So if I have a signature S1, which defines a type T1, and one module M1, which is of this signature, and it's the only instance for that signature. I then define a second module type, S2, and 2 modules for this signature with different types. And I have a targeted signature sol and a functor that will generate this module type with a cool feature and takes 2 arguments, x and y. Both define the same type, but x is of signature S2, which has 2 solutions, and y is of signature S1, which has only 1 solution. And then I'm going to start a search to look for my signature with a cool feature. So, and doing this in the context where I have all the modules presented above. So I have my initial state for search, where I'm not looking at any modules, and I also have a set of modules in the context that I can look at. And I have a first role as focus, which allows me to take a module from the database and start to look at it by moving it into the focusing point. So I can use this role to do a reduction on the state. But then my module M1 defines a type T1 when SL requires a cool feature that M1 does not contain. So I can use another role which drops away M1 to forget about it and be able to continue the search with more interesting modules. So I can just forget about M1. In the same way, M2A also is not valid for the targeted signature, so I can use the two rules presented before to forget about it. The same for M2B, and then I can start looking at F2 implies 1. So now I'm looking at F2 implies 1. So this module is a functor. So to infer that this functor is actually a valid solution, I will need to infer its argument. So I can use another rule that opens the application by creating a search for the two recursive arguments. In those search, so if I take the example of y, I still have the name y, which is typing artifact, and the targeted signature. But this inference happens in the context where I have x, because there is a telescope in functor arguments, and the first argument is known by the second argument. So I have a local extension of a context. I also have the initial state of a search, where I'm not looking at anybody, I haven't found any solution, and I have a set of modules from the context that I can look at. And also, for termination criteria, I also know on which signature the functor was called, so that all new calls to this functor will ensure that they are strictly decreasing. So with this state, I can start to try and infer the argument. For this, I have a rule saying that if I do reduction in one of the arguments, I can apply this reduction on the whole. And I can then do a huge amount of reduction to infer all possible solution for x, which is M2A, M and 2B. But then I have two solutions that are not the same, and you could say that the search has failed because I have an ambiguity. But we also have a second argument, so we're going to look. So this creates a new state for first argument. Then we can look at the second argument and use once again our rules to reduce it to only one solution, which is M1. And M1 also defines that T2 is of type int because we have a constraint between the signature of y and the signature of x. And this becomes the new state of our search. So we have this information inside the argument y, that the type T2 in x must be int. But this is local to the argument. But we have inferred this argument fully, meaning that if we have an actual solution for this functor, we need to have this constraint to be valid. So we can extract this constraint from the inferred argument to move it to the application because it's a whole rule for the application. So we can do a reduction by lifting the constraint out of this argument and having available for more people. And then we have this new constraint, which X is able to look at. So we can use it to reject the solution M2B because it defines that T2 is low. And because both constraints are incompatible, this means that this solution is invalid and we must forget about it using the rule sFilter. So we can forget about it and have only one solution for X. Meaning that now we only have one solution for both arguments. The solution for X is M2A, the solution for Y is M1. meaning that we have fully inferred all arguments for this functor application, and that we can solve the solution by extracting all the solution from each argument and building a modular expression from it. And now we have a valid solution, which is the functor applied to those arguments that have been inferred. And this is the solution from the search. But in practice, we have a few subtleties with the implementation because we want to be efficient. And we need to have several optimizations to quickly filter out subtyping failures. So first of all, we have a constant time selection of all modules implementing the most significant recurred field by just accessing the database. Then we have a constant time shallow subtyping approximation by only looking at the field names. We are not going more inside the signature to look at the type that are defined. We just check that all the names we want are actually inside the signature. And then we can do a quick structural approximation of subtyping to reject the last failing example that have passed the filters that happened before actually doing the final subtyping, which is much more costly, but at least we hope that we don't do it too much because most invalid examples will already have been rejected. So, as a takeaway, so we have a formalization and an implementation of implicit modules that is incomplete because we have a problem of decidability of when we're terminating, so we don't have every example that are accepted. But it is designed to be expressive in practice by accepting lots of examples and not adding any constraint of the order of the argument synthesis. And we also avoid word duplication and backtracking to be efficient. This framework has been also designed to be customizable. We can modify the termination check, but we can also add new reduction rules to cover a few more cases. And the elaboration of modular expression is much more complex than for type classes inference, and this is why we need such a huge set of rules to be able to infer things efficiently. But we still have the problem of fixing the interaction with a core language in order to be able to have a mechanism proudly say that it emulates type classes in a modular language. Do you have any questions?
Thank you, Samuel. We have about 5 minutes for questions, so please come up to the mic.
Hey, thank you for this. I'm very excited to get modular implicits in OCaml, so thank you for your work here. I'm curious if you could talk a little bit about what you think the scoping rules should be for like what implicit modules and functors should be like in the search space, because I know that like in the world of Scala, for example, this is something that frequently causes people headaches.
Yeah, so one thing that's extremely important for modular implicit is that compared to Scala implicits, is that if we have multiple solutions, if there are multiple, we reject the example. Whereas in the opposite, Scala, if they have multiple solutions, they take the best one. After what we put inside the context, that's, I think, more global decision, but we have also still the problem of if we add too many things, it becomes much more difficult to understand what the program is doing. But modules have much more structure than core language values. Like we can actually give a name to a field, and the name contains information, not just a type.
Thank you.
Does this respond to a question?
Yeah, thanks.
Thanks for the talk. So I was wondering how the search procedure compares with Scala, and specifically regarding the termination criterion, because Scala has its own criterion that seems to work well enough. You have something that looks more complex. I think in Scala, you just make sure that the size of the query type doesn't increase, and that's pretty much it, as far as I know.
The thing they have in Scala is you infer type, And so the type might be just decreasing. Whereas with modular implicits, we're inferring a signature, and we can just change fully from one signature to the other, like completely switching from a problem to the other, saying, oh, I wanted to infer arithmetic, but I realized that I can just infer the whole arithmetic if I have another property. And the question is, do we actually want to compare both properties? And do we want to, when we're comparing two signatures, we have a whole set of types inside a signature. And so we can, do we consider that all types in the signature have the same weight for termination?
I'm not sure because I'm not sure how it compares, but it would be useful to have a proper comparison. And regarding the scoping question, I guess what I wanted to ask is, where do you look for these functors? Is it just everything that's in scope, or do you look at things that are not in scope, like that things associated with the types?
We only look at things that are in scope, but when adding something in scope, we ask for an annotation saying, can we use it as implicit? So we don't take all the functors. We only take the functors in scope that have been labeled as usable.
Manually import all the functors that could participate in the resolution?
Yes. Yes, or opening libraries that define them, but in the library they say, oh, this one, you can use it as such.
I think we have time for one more question. Well, maybe the next speaker can already come up. And I want to invite all of you to join us here in the front rows if you want to sit down. There's still a bunch of space available.
Yeah, my question is about, so you have this restriction that there must be a unique solution, right? Which seems to me to have the implication that you lose the weakening property of the type system. So meaning that a program that is well-typed could suddenly become ill-typed by adding some definition to it that is not actually, it doesn't actually depend upon. Do you consider that a practical problem from like a compositionality or a software engineering perspective, or are you just okay with that?
It's indeed a problem we know that exists. We hope that in most cases we have multiple instances of signatures for various type. And so we don't happen to have many cases where we infer type based on the fact that there was only one solution, and that it's more that we have only one type that is valid, and from this we're able to infer the solution.
Okay,
but
thanks.
in practice, that's actually a problem.
Okay, thanks.
Let's thank the speaker again.